All right, 7.4, using normal distribution. Okay, so one thing I want to point out is that we said in the last video that the mean is this X bar. Sometimes you'll also see it written like this, like a weird M for mean, or it's like the mu symbol. You'll hear it pronounced. This is, you would say it like this, mu. It doesn't matter. Just want to let you know to look out for both of these symbols. Okay, here's what we need to understand. If something is normally distributed, okay, if it's normally distributed, that means that all the data falls within these certain categories. And we have this percentage breakdown. This is just by standard deviation. So here's your mean. I'll zoom in on this. Here's your mean right here. And then look, it's saying if you subtract one standard deviation, if you subtract two, subtract three. If you add one, you add two, you add three. So within one standard deviation from the center, it'd be 68%. Within two, 95% of the data falls within there. And then within three, 99.7%. Now there could still be outliers, but it's a really, really small percentage of the actual data. And then that breaks down proportionally here. So instead of 68, you could do 34, 34, 13.5, 13.5, 2.5, or not 2.5, 2.35. And then everything after that third standard deviation is only 0.15%. Why does this matter? Well, you're going to get questions like this. Example 1. A normal distribution has mean and standard deviation. For a randomly selected x value from the distribution, find the probability that it's the mean. This means the probability of the average minus one standard deviation, that this is somewhere in between. So what this is saying, this x is somewhere in between. Take away one standard deviation or add 3. All right. What is this asking? I'm going to just kind of like show you this on a highlighter. What they're saying here is if we're going to go from here to here, they're saying go to here all the way to 3 standard deviations over. Or another way you could think of it is it's going from here to here. Well, all they want then is for you to just add up all these different probabilities. They're just saying, what's the probability that it falls within this range? So if I was to kind of like map this out for you all, right, here's my mean. And then here's the mean minus 1 standard deviation. And here's the mean plus 1 standard deviation. The mean plus 2 standard deviations. And then plus 3 standard deviations. And again, I'm just trying to find when does it fall into this range. Well, they tell me all the percentages. They told me that this is a 34%, this is 34%, this is 13.5. Again, every set of data that's normally distributed will fall within these categories. So as long as they say it's normally distributed, we already know the breakdowns. And then this last one is 2.35. Now, if they ask me to go past this, it'd have to be 0.1 or 0.15, yeah. Now, so what's the probability that it falls in there? We literally just add these all up. 34 plus 34 plus 13.5 plus 2.35. And we add that all up and we get 83.85%. So there's an 83.85% chance that it falls within this range, as long as the data is normally distributed. All right. Example 2. The score of exam for an entrance to a firefighter program are normally distributed. Okay, voila, it fits this curve then. With a mean of 200 points. Oh, I cut that off. And a standard deviation of 20 points. Okay, so we could actually kind of make a little chart here if we wanted to. I'm not going to do the whole bell curve thing. I'm just going to do this. Oh, by the way, this, if you haven't ever heard of this before, this is called a standard bell curve. Because in normally distributed data, it makes this like bell-shaped curve. It's also called a Gaussian curve. And yeah, you get to play more with this in like upper calculus. But for now, it's just a way to represent data. And it turns out, again, normally distributed data, majority of it will fall right in this first category within 1 standard deviation of the mean. 68% actually. So let's take a look. Well, what could I do here? Well, I'm just going to make like a little table. And they're saying about what percent of the candidates score lower than 160 points. So here's what we're going to do. I'm going to make a little table. I'm going to start with the mean, which we said is 200. That's going to go right here. All right, and then like kind of like a number line. So then if the standard deviation is 20 points, then this would be 180, this would be 160, this would be 140. Over here would be 220, 240, 260. And I'm going to make like a little chart. And notice I just started the mean. I went 3 this way, 3 that way. And we already know percentages, right? We already know this is 34. These are all percentages. You could write the percentage symbol if you want. Oops, sorry about that wrong. That's 2.35. And then this is only 0.15. And this is 34, and this is 13.5. And this is 2.35, and this is 0.15. Now this question is specifically asking about what percent of the candidates scored lower than 160 points. So lower than 160 is just this area right here. So literally all I'm going to do is say, okay, well, I just have to add up 0.5 plus 2.35, and that'll give me 2.5%. That must be my answer. Only 2.5% of the people who took this test are going to score less than 160. All right, what about this next question? This one is going to use the same data table. It says candidates with scores above 220 are admitted into the training program. About what? That's obviously a typo. Percent of the candidates are accepted into the program. Okay, so how many scored above 220? Well, that's this group right here. So once again, I'm just going to add these all up. I would have 13.5 plus 2.35 plus 0.15. You add that all up and you get about 16%. And we're saying about here because it's not always going to be exactly 16%. It should be very close to this. So when we say that the data falls within this category, we're making some assumptions. You do have to have a certain amount of data to be normally distributed, but it might be 15.8 or 16.1. So, or it might, for this question, it might be 2.4 or 2.7. So we're getting about, because, you know, life is a little bit messy, but this helps us approximate where things are going to end up. Okay. All right, let's go to the next page. So now let's talk about standard normal distribution and z-scores. All this is a way of looking at the same data we just looked at, but now we're just going to call this 0 the mean. And the z of 1 would mean 1 standard deviation over, 2 would be 2, 3 would be 3 over. Negative 1 would be 1 to the left, 2 to the left, 3 to the left. So it's really the exact same thing that we just did, but we're going to call it in terms of a z-score. And we have a little formula for the z-score. You take your position or your data point, subtract it from the mean, divided by the standard deviation. And if it's negative, it's obviously going to be this way. And if it's positive, it's going to be this way. And that makes sense, right? If your value is above the mean, it's going to be in the positive side. If it's below the mean, you're going to get a negative side. The z-value for a particular x value is called the z-score, and is the number of standard deviations the x value lies above or below the mean. And then what we have right here, this is a standard normal table. And you actually could find some of these that go to even higher decimals. But what we're saying is if some piece of information, some data set has a z-score, like let's just say, for example, let's say the z is negative 0.4. That's what's listed here. So you see we have a 0 and we have a negative 0. And if we wanted to find the probability, and it says right here, if z is a randomly selected value from a standard normal distribution, you can use the table above to find the probability that z is less than or equal to some given value. So z-score of negative 0.4, we have negative 0 here, positive 0 here, right? And then we just find the point value right here, so it's 0.4, and we would get this value that this correlates to a 0.3446 probability, which you could also, which is the same thing as saying like 34.46%. So what we're saying, depending on the context, is that you could use the table to find the probability that z, that this situation is less than 34.46% or equal to this of happening. Okay, so this is how you can go from a z-score to a probability. So that was more just to show you how to read this chart, but let's put it into practice now. So now they're going to give me a z-score. And really we should go ahead and just like change all these in example 3. These should all just actually be z's. Let's just say they're giving us a z-score. How can we read this table? Remember, this is less than or equal to. That's really important to keep in mind. Okay, so if I wanted to do 3.5, so the first thing I'm going to do is I'm going to just find 3.5. So 3 is right here, 0.5 is right here, and so it'd be right there. And notice what it says. It says the probability that it's less than or equal to 3.5. Well, we end up with 0.998. So we could say that there's a 99, oh, sorry, that's a 98. There's 3 nines. 99.98% chance that this would be true, that our z-score is less than or equal to 3.5. So that would be our answer for this problem. All right, now what if it's less than or equal to negative 0.7? I think you guys can figure this out. In fact, I want you to just pause the video and try example 3 part B on your own right now. Okay, so you should have found the negative 0 here, the 0.7 here, and you got 0.2420. So that's 24.2% chance. So what are we saying? We're saying the probability that the z-score is less than or equal to negative 0.7 is 24.2% chance. All right, now on this one's a little bit funky because this one says that z is greater than or equal to 1.2. And that's going to be a little bit tricky. What I'm going to say instead, let's just do this. Let's just say it's greater than 1.2. Well, let's first find the probability, or let's think of it like this. The probability that your z-score is greater than 1.2 would have to equal the probability, would have to equal 1 minus the probability that my z is less than or equal to 1.2, right? So if this accounts for all the times when it's less than or equal to 1.2, and 1 is the whole amount of probability, I just subtract it. Like basically what I'm saying is this probability here and this probability here should add up to 1 whole. So what we're going to do, since we're not finding the less than or equal to, because that's what this chart gives us, less than or equal to, we're gonna find less than or equal to and subtract it from 1. So let's go ahead and do that. Let's find when the z-score is 1.2. So here's the 1, here's the 0.2. And so essentially we found this part to be 0.8849. But remember, that's not what the question is asking. It's asking for the probability that z is greater than 1.2. So I'm going to do 1 minus that. And like I said, really we should have just said greater, not greater than or equal to, just to make this make a little bit more sense. Okay, so 1 minus 0.8849. Well, if I do that math, I end up with about 0.1151, which means that my answer that z is greater than 1.2, the z-score the probability to find z-score greater than 1.2 is 11.51%. All right, again, this is really just the same thing, but now all we're doing is we're getting more specific. We could be more specific. So before we could only say like 34%, 34%. Well, what the z-chart lets us do is like get to a very specific part somewhere in here, as long as we treat all the standard deviations as z-scores. We'll play with this more in class if you have questions, but it's really simple. You're just reading this chart and interpreting what it means back. And I think after you do it a few times, it'll make a lot more sense. All right, let's give one last tricky problem here to see if we could figure it out. So we have a survey of 20 colleges, found that the average credit card debt for seniors was $34.50. So that to me sounds like a mean. The debt was normally distributed. Okay, that's key. That means that we can use our basic bell curve with a standard deviation of 1175. Okay, so there's my standard deviation. That's going to be important. Find the probability that the credit card debt of the seniors was at most $3,600. So at most, actually it's not x equals. We're saying that if it's at most 3,600, aren't we saying it has to be less than or equal to 3,600? So really we want to know the probability that that value is less than or equal to 3,600. Okay, well let's just convert this 3,600 to a z-score. All right, we have this formula up here. let's use it, okay? So what would the z-score of this thing be? The z would be, my value is 3,600, minus the mean. We know the mean is 3,450, divided by the standard deviation, which we know to be 1175. Subtract the top, you get 150. And then 150 divided by 1175 gives you 0.1276595,745. Okay, look at all these, how specific we can be with the z-score. The problem is the chart I've given you only goes to 1 decimal place, okay? So we're not going to be able to go that far. We're not going to be able to be that specific. But that's okay. So really, what's the closest one if we go to 1 decimal? Well, it would just be 0.1. And it's already saying, the question's already phrased as less than or equal to, so I don't have to worry about this whole thing like I did before. I'm just going to use that less than or equal to calculate the appropriate percentage. So we just got to find 0.1 on this chart. So let's go up here and see if we can find it. Here's 0, here's 0.1, I got 0.5398. So let's copy that down. So the probability that x is less than or equal to 3,600 is 0.5398, which is the same thing as saying 53.98%. Okay, now there are charts out there that are more specific than this, that we could get into 2 decimals or 3 decimals even, but it just gets crazy and really complicated. So all I'm really asking you to do is to do it to 1 decimal place. So this is as accurate as we can be. Now, we do know that it's a little bit more than this, right? Because it's not actually 0.1, it's 0.127. So it's really close to like 0.13. So what we could do, just kind of showing, we know that it's somewhere between, here's 0.1, and then somewhere between 0.1 and 0.2. So it's somewhere between this 5398, which is basically 0.54, and this 0.5793, which is basically 0.58. So since we know it's a little bit more than this, and a little bit less than this, and it's closer to this number, we could also just do an estimation, and we could just kind of say like, we could also say it's about 55%, right? Because it's a little bit more than this number, which is pretty much right at 54, but not quite to 0.2 yet. So I would just say it's about 55%. Both of these are fine answers. Again, we're just like approximating here. We don't have a specific value because our z-chart can't be that specific, but we're just using that chart to help us. Hopefully that makes sense. If not, ask me about it in class. Happy to go over it. And I'll see you guys on the next video.